So this video is going to have us go through the different vocabulary words and general wave concepts that we're going to be using for this unit. And so at this point in time, we should have in our hands some PowerPoint notes with some blanks that we're going to fill in as we go. So this is our first heading here. So the first few sheets of the notes, we're going to look at different types of waves, different ways in which we can classify, categorize waves, and then all the different parts of a wave that we can analyze. And so that's going to determine different properties as we continue on with the unit, like pitch and how loud a wave is. So we'll kind of experience that type of phenomenon, how changes and certain variables can determine what kind of wave you're going to perceive and hear, every day. Waves in general, though, they come in a variety of different shape and forms: light waves, sound waves, water waves. So what makes something a wave is how it moves. So it's a disturbance. And here a little bit more. So disturbance with a rhythm that carries energy through matter or space. So a disturbance with a rhythm that carries energy, through matter or space. So that disturbance that you make is some sort of application into the system. So you're creating energy into the system. And so then that disturbance occurs over and over and over again with a rhythm. So it's repetitive. And this particular disturbance, waves, so energy can travel through matter, through the medium, but it doesn't move matter. So it just carries energy. It doesn't move matter. So it doesn't move anything physical. Most waves need a medium. They need some sort of matter to travel through. Even just air, the gas, is considered a medium. But there are a few waves that can travel through a vacuum. And so we'll talk about those different types of waves as the year goes on. When we're analyzing waves, it's generally useful and suggested to analyze a wave at a time. And since it's a rhythm, you just need to look at one wave. And once you analyze all the different properties of a specific wave, then you know that it's the same for every other wave that's made after that. So when we analyze waves, we generally just look at a single wave pulse, which is a single disturbance and so in this case, just a single wave. That we analyze. So let's say I have a rope attached to a wall here, and I'm holding the rope. Before energy is put into the system, into the medium that the wave's going to travel through, so in this case, the medium is the rope, you see just a flat line here, so no energy present. So I can put energy into the system in the form of kinetic energy, so moving, by causing a snap in the rope. And so that snap is going to create a wave pulse that's going to carry energy as it travels throughout the length of the rope. So a wave pulse is just a single bump disturbance that's being made that we can analyze. It's going to carry energy through matter in this case, or space. We have two types of waves based on how the wave is made, how the wave is generated. And for most of the year, we're going to be looking at different types of transverse waves. A transverse wave is a wave that vibrates. Perpendicular to motion or to the disturbance. So a wave that vibrates perpendicular to motion, perpendicular to the disturbance. So this means whatever is causing the wave to vibrate, perpendicular means that we're at a 90-degree angle to the vibration. So in our Slinky lab that we did, so if you applied no energy to the system, your Slinky was just flat. It would just lay straight across. In order to get that Slinky to move to create a wave, you would move the Slinky up and down. So you would shake it up and down, and that caused the wave through the Slinky to travel left and right. So you move up and down, but the wave goes left and right. So it's at a 90-degree angle to each other. Towards the end of the lab, this part went kind of quick, but you were also asked to make our other type of wave called a longitudinal wave. A longitudinal wave, so this is a wave that is generated when a disturbance, so again, your disturbance being whatever that energy is that you're putting into the system. When a disturbance is in the same direction as the wave. So when a disturbance is in the same direction as the wave. We also sometimes call these compression waves. They're called compression waves based on how the wave looks. So using a Slinky again, we can make a compression wave. And again, you were asked to do this in the second day of your lab. But if I took my Slinky and I moved it forward and backwards, then that would create a wave, a series of compressions and expansions that would travel side to side, and I'm also pushing side to side along the length of the Slinky. So instead of the wave looking up and down, the wave is traveling in areas of compressions and expansions. So you have particles that are compressing and then bouncing off of each other, compressing, bouncing off of each other. So that causes the wave then to travel down the length of the Slinky. So they do look very different side by side. So a transverse wave has this up and down, high and low point look. Longitudinal waves has areas of compression and areas of refraction, which we call it, or areas of expansion. Sound is a common example of a compression wave. So the speaker vibrates, that compresses some of the air around it, but it also pushes some of the air out away from it. And then that compresses some air particles, also causes them to expand, or not expand, but to push out. So you have these areas of compression of matter. And then refraction is that empty space. And so you have particles pushing and bumping each other along using air as a medium until that air reaches your ears. Now, when we analyze waves, both of these properties, all these properties we're going to talk about, we can use longitudinal waves for, but they're a lot easier to analyze with transverse waves. And so a wave that is at rest, so there's no energy in the system, the Slinky's just flat laying on the ground. We call that wave at rest to be at the mean position. So the mean position is basically like a line that divides the wave in half. And This also is sometimes referred to as the equilibrium line. And so this is the wave at rest. So there is no waves being made. There is no energy in the system. And so how far apart the wave is from the mean this way or that way can help us to determine quite a few different things about the wave, all relative to this mean position or this equilibrium line. So a lot of vocabulary with this unit. The first one is amplitude. Amplitude is a way to describe the displacement of the wave from rest. Displacement of the wave from rest. Another way how people like to describe or visualize this is how high, like how tall the wave pulse is. So in this wave here, and this line here is my mean position, or the equilibrium line. And so I'm measuring amplitude from this line to how high it is displaced or how low it is displaced. So amplitude is a measurement from the high point to the mean. I can also measure amplitude from the mean to the lowest point. So this is the displacement from rest. A higher amplitude means that the wave has more energy. Or if you put more energy into the system, into the wave, it's going to create a wave with a higher amplitude. And so we saw this with our Slinky lab. If I just lightly shake the Slinky up and down, the waves don't go as high. If I really shake it hard, then the waves go really high up. We see a really high displacement. So higher amplitude means that you have more energy with the wave versus one with a shorter amplitude. Another property that we can analyze in waves is the wavelength. So this is the length of the wave until it repeats itself. And waves are rhythmic, so we're going to generally see multiple wavelengths within a picture. And we can measure wavelength, so how long a single wave is, at a variety of different points along the wave. So we're going to start at one spot on the wave and measure until the wave becomes repetitive. So we see that new point again. So with wavelength, and actually here I have a variety of different points we can measure down here. I'm going to first cut this in half and draw a equilibrium line or a mean position. I'm using it interchangeably because you're going to see it described or labeled both probably about 50-50. So this equilibrium line, mean position, that's going to cut this wave, in half, and I have my disturbance here. So to figure out how long the wave is, I can measure it at 3 points. I can measure it from crest to crest. Crest is the highest point of a wave. So the high point of a wave, the tallest point. So it's different than amplitude. Amplitude is a measurement of the entire distance from here to here. Crest is just a single point. Here's the highest. So it's until it repeats itself. So I can measure from crest, and then all of this is a single wave until I get to another crest. Now I'm getting repetitive again, so I would stop here. I could also measure from trough to trough, which is the lowest point of a wave. So if I were going to go from trough to trough, I can kind of extend this out here. So I can measure from low to low. So here it goes up. This is where it goes up again. So this is where the repetition is. So I could go from here to here. Generally, it's the easiest to measure away from like where it starts. So like trough to trough wouldn't be bad either. Another way that you can measure wavelength is from our third spot, from the mean position to the mean position. So where does it start on the mean and where does it end on the mean? Now, if you're going to go from mean to mean, or equilibrium line to equilibrium line, we want to pick a place to start. So this spot here, this is where I'm going into a crest, starting to go up. So I'm going to measure until I go into a crest again. So I wouldn't stop here because it's not repetitive. Here I'm going up, here I'm going down. I would stop here and I could measure from here to here where I start to go back up into a crest. So even just visually, you can kind of see that it doesn't matter if I'm from here or measuring from here to here, or if I'm measuring down from here to here. Since the wave is rhythmic, it's repetitive, it should be the same over and over and over again. I just need to measure in one spot, and the wavelength should be the same no matter where I'm at, no matter where I'm measuring. Now we're going to get into some variables that will involve some calculations here as we go. So we will have a few equations that are going to go with this unit. First thing that we can calculate, and we'll see that equation in a minute here, is period of a wave, specifically how much time, so it's a time period, that it takes for a wavelength to occur. So generally I'm given a time frame, and it's usually a second's worth of time. And within a second's worth of time, how much does a single wavelength happen in? Your frequency. So frequency, if you think of how frequent something is, we're thinking of how often it occurs. So this is the number of oscillations. So ups and downs or compressions that a wave makes each second. So how many wavelengths do you have in a second's worth of time? How many oscillations, another way of saying it, do you have in a second's worth of time? So what we're looking for is, here's my second of time. So how many waves do I have being made within that second's worth of time? So a high frequency wave will have more oscillations, more wavelengths in a second than one with a low frequency. And so to count, generally it's best to count. You're going to count each wavelength based on how the wave starts. So here it starts on the mean. So I can count from the mean how many wavelengths I see. So I see 1, 2, 3, 4, 5, 6 waves here. In a second. Whereas here I have 1, 2, 3 waves each second. So your time period is, okay, here's the frequency, how many waves I have. So I have multiple waves occurring in a second's worth of time. So how much does a single wave occur within that second's worth of time amongst all these waves? And then frequency is what's the total number of waves occurring within the second. So to solve for wave frequency, we call this the wave frequency formula, but we can use this to find wave period too. So the wave period, so the time period or frequency. We can use the following equation. So the equation starts with frequency is equal to just a 1, so the number 1, over a period of time. So 1 over t. And if I wanted to find the time period, I would just flip the t with the f, so 1 over the frequency. So they are related to each other. If you know the 1, then you're just taking 1 then over the other. Since for both, we're using a second's worth of time as like a benchmark here. The units for frequency we call the hertz, like the rental car. And so we shorten that with an HZ. And units for time are an S for seconds. And the symbols are, go along with the name, so that doesn't make that too hard to remember. So F stands for frequency. And then the T stands for time. So you have a blank slide here that we're going to use to do just a quick practice problem to see what one of these problems might look like. So let's say that we have so a wave is made to have a frequency of 3.33 hertz. So a wave is made to have a frequency of 3.33 hertz. How much time does a single wavelength occur in? So how much time does it take for a single wavelength to occur? So if my frequency is 3.33 hertz and I'm looking for the time, then all I have to do is take 1 over 3.33 hertz. And so my calculator, 1 divided by 3.33, that gives me about 0.3 seconds. So in 0.3 seconds, a single wave will occur within that second's worth of time. We can also figure out how fast the wave goes. And so we did this in our Slinky lab here. So we can use this to find the wave speed or velocity if the problem specifically says velocity. Speed / velocity. We have wavelength and frequency that we can also use for this equation. So this one's just a friendly multiplying one. So we have V equals F times times this funky little shape here is called lambda. V equals F times lambda. In this equation, V stands for your velocity or your speed. Units for that are meters per second. F stands for your frequency. And units for frequency are just like in our other formula, the hertz. And so I do have two problems that I can use to solve for frequency. So this is where guess comes in. Say, do you have wavelength and speed, or do you have time? And that's going to determine which equation you can use. And this little lambda here is the wavelength. And just like any distance length measurement that we use in here, we're going to use meters for a wavelength. And if you need help pronouncing the symbol here, it's pronounced lambda. So we'll have one more problem here with this equation, and then we'll call that it for our notes. So you have your last slide, which is another blank. So we'll try to keep this one just short and sweet as well. So let's say we're asked to find the frequency of a wave traveling at a speed of 338 meters per second. If each wavelength is 1.29 meters long. To find the frequency of a wave traveling at a speed of 338 meters per second if each wavelength is 1.29 meters long. So going through the problem, writing out my givens and unknowns, doing my guess steps here. So find the frequency. So F here is my unknown. Find in frequency. I have a speed of 338 meters per second. So this is my V. And then wavelength, lambda, 1.29 meters. So lambda, 1.29 meters. So I'm asked to find frequency, but since I don't see any time in seconds, I'm using wave speed. So V equals F times lambda. So this is set up to solve for wave speed, which I have. So I do want to rearrange this to solve for frequency. So opposite of multiplication is division, and I want to keep everything balanced. So what I do on one side, I do on the other. And so if I want F by itself, then I need to get rid of wavelength here. So cross that off. So V over lambda will give me the frequency. I can plug in my numbers here. So 338 meters per second over 1.29 meters. Divide that out. And so you'll be getting 262 hertz as my frequency here. So that is it for our notes for the day. So we're going to do a more simple introduction here for the first day, and then keep these notes handy, and we'll be using them quite a bit tomorrow, getting a little bit more practice with our vocabulary and practice with doing practice problems with these new equations here. If we have any general questions after the notes, feel free to send me an email. Otherwise, we're all set with our notes for the day.